it's going to be hard. Anyway, let's set the stage for today. Okay. What we did last week. Normally, we started talking about sequential logic. And we said if we want to have advanced secrets, we need to keep state of the system something. That came to our mind. What about to make memory? How we can make memory? Good. If it's backing, then it's not nice. Okay, so I think it's better. Anyway, we said we need memory. Okay, I just answered that, but I want to ask you why we need memory. I want to ask you guys here what we need memory. Any idea? Why we need memory?
Store things.
To store things. Okay, that's good. You tell me why we need memory.
To store data.
Same, something else to make our circuits more advanced, to save a state. That's the main point. We want to save a state. Who knows what is a state? Okay.
And I can make a guess.
You can guess.
A state is a system in a point of time. It is a system with certain inputs, a certain output, saved at a time.
Okay. Time involved. Okay. Any other response regarding the state? You want to answer? Is the state a system or just a number, like numbers?
I think it depends on your scope, right? It depends on your scope.
But most of the time, any response? You want you answer? You? A state on and off for some systems can be. Any other, look this area. What about you? How are you? So what is a state? Like what is the state of you here? The position that you see showing you the state. Okay. So the position of the system showing the state of the system. So in general, the state is some values that summarize the system. It's not the system by itself. It's some values that summarize the system and minimum values. Okay, so the state of the system is a minimum values that summarize the system. Minimum values that summarize the system. Okay, so that's a state. And we need to keep this a state because maybe we want to design a system that act more advanced, like make decision based on paths. So we need to keep those paths somewhere. That's why we need memory for minimum systems, like this system that we are designing in this digital logic class. But in general, to save, data, or they are all correct. If we have computer, we want to save data. But in our points of view for systems that we are designing in digital system, we need memory to keep a state of the circuit. A state of the circuit is the minimum information that can summarize that system. Okay, so we need memory. Okay, that's good. How make memory? Okay, do you remember anything about, I think 2 weeks, 1 week ago, we talked about memory, how we make memory. Any idea, again? You remember how we make memory?
The C flip-flops.
Flip-flop is the end, at the beginning. Any other? Yeah, of course, we're gonna get to flip-flop. Yes.
We wire the outputs to the inputs.
Yes, making loop. Very good. Making loop. When you make a loop, you have memory. Why? Because this loop can have some information that passing, electrons passing can be 1 or 0. So you just need to make a loop. How we make a loop? Last class, we learned you just can put 2 inverter behind each other and make a feedback loop to make a loop. And then we made it more advanced and we said, okay, what about we just have 2 NAND gates. Good. Okay, so we said we need to have a loop, but we can wrap that loop around and make something like that. This is, yes. Oh.
I thought I could still get that.
Oh, okay, yes. It has a little delay. Okay, so we can have 2 NAND gates and make a loop like that. And this was the last part that we mentioned. We said this, we call that latch. Why latch? I mean, that you know. And this is the structure of the loop that we can make. And we said, okay, we can save something here. We call that Q bar and Q, the value inside. And that's called latch. Why it's called latch? Because it's actually level active. So it works based off the level, and we don't have clock. So this was the last part, the last things that we mentioned about memory, and we called this structure SR latch. SR latch, S is for set and reset. Okay? And we said, okay, look at that. From the output, we got input. And so if R and S at the same time be 1, what's going to happen? If this is 1 and this is 1, here we're going to have 0. Here we're going to have whatever was here. Q was here, Q bar here. So Q and Q bar are going to stay there. So 1 and 1 is, okay, so here we're going to come back to state. So we're going to say, okay, one input, make the state of this, the latch Q. So that's one of the states for this latch. So the Q is the value inside that. It is 1 and 1, so it acts as a memory. Any question about this 1 and 1? Do you know why 1 and 1 make it memory? I just mentioned, but I'm gonna make that deeper. The reason is because of AND. If you AND anything like A with 1, A gonna pass. That's why here we AND and then not it, so become NAND. We AND 1 with Q. That's why Q passing, but after make it not or negate, We're going to have Q bar. So that's why it makes memory. So if it's 1 and 1 as an input, this latch acts as a memory. So this is what we wanted. We wanted to make a memory. So how make memory? Just make input 1 and 1. What about 1 and 0? If it's 1 and 0, imagine this is R and S. If it's 1 and 0, what's going to happen? If it's 1 and 0, R is 1, so Q passing, but S is 0. So if S is 0, again go back to the AND. If you AND anything with 0, what is the output? What is the output? Always 0. That's why the 0 going out and coming back there and 0 is staying. Reset. And if is 1 and 0, what's going to happen? So if in this time it's set, what's going to happen? Let's see. For S is 1, so here we have Q bar here. Q bar here, and here we have so S is here 1, okay, S is 1, maybe I write it here, that I clean up, right? So R is 0, and S is 1. So what's happening? After AND, here we're going to have Q bar. That's going to be Q. But what about this part? 0 after AND is going to be 1 here, because it's going to get NOT. And 1 going to come back here, and all the state going to get 1. So this is three states that we have for this register. One is Q, that is memory. One is reset, and one is set. So these three are three states that happening in this latch. Didn't tell you last time, but if you have a system like that, even you have a state diagram. You can draw a state diagram for that. Yes, what is a state diagram? It's a diagram that's showing a state memory or Q, state reset, and a state set. And you are moving from state to another state based on what? Yes?
I just have a question. So this is for an active high SR latch, correct?
Yeah, active low. This is the last part that we mentioned. That's the active low. Yeah. Active low means when the reset is 1, is reset. However, for both of them was like that, but the operation was different.
So if it's active low, then would those be flips? You know, like if R is 0, then you would be resetting, and if S is low, then you would be setting if that's active low.
Setting and resetting, acting exactly with this. If reset is 1, is reset. If it's set is 1, is set. Yeah, but this is active low. But don't worry about that part now. In this flip-flop, doesn't matter. In this latch, doesn't matter it's active low or active high. This is the truth table or a state table, because it's showing a state now, and we have 3 states. Don't worry about active low and active high in this case. So these 3 states makes a state diagram. And what if it changes state? I want to draw between this and this something. How reset change to set, or reset become memory? What? What changed the state? Any idea? Input. When input coming, changes state. when input coming, change the state. So what inputs we have? Okay, from memory to set, from set to reset, from reset to memory, from memory to memory. So if, for example, 1 and 1 coming, memory stay memory. If reset, I consider R and S. So if R01 happen, and if for set, from memory to set, it should be the other side. You're gonna have all of these connections. Because I'm not gonna write all of them. Like for example, reset to set is 0, 1, means set is 1. And for all of them, these 2 bits are input. And this input is define how we do transition. We call that transition. Transition between 2 states. Okay. So that was what we learned last class. And today we want to continue. We had problem with this latch. What's the problem with latch? Do you remember?
Invalid states.
Yes, one of them was invalid state. If there is 0 and 0, this is gonna make Q bar and Q equal. That's not gonna happen. That's invalid. So being invalid state is one of them, but it was another problem. Race condition. Yeah, race condition saying if these inputs at the same time changing is gonna make race. What race means? Race means the delay between gates. Change the system. These 2 NANDs are like, if you want to design them, you need to go with like transistors. And these transistors passing electrons, and these electrons, they're not going all in the same speed. So there is some delay between these gates, and this delay make like some actually, what can I say? They are not synchronized. They are not synchronized enough, and this synchronization makes this unstable. It's not stable anymore. In that time, it's just fluctuating on and off. So this is called race condition. Why we call it race? Because they are racing to pass from those gates, and any of them pass faster, that's going to change the system. And it's going to make unstable system, or going to make glitch. Glitch was those spark like this, going up and then become stable. So this is called glitch. This is a problem for the system. And we want to see how we can solve it. Last class we said, what about we put some control for latch? Okay, let's clean up this a little bit. We said let's put some control instead of putting R and S directly to the latch. Make some enable signal and have another set of gates. And for example, here is R and S, and have enable. That can help. That can help. At least enable can give some control to the system, but still there is problem. The problem is this enable, this system is level actually active. That's the main problem. Here we can change the color of this. Okay, Anyway, this is level active. That's level active. That's the problem, because when it's level active, you have lots of possibilities in those levels. If input and output kind of having feedback, this gonna make trouble. Being active in a level is problem. We need to be active in very short time, like we make pulses like this. Do not let the system actually fluctuate or not be stable. This is the idea of flip-flop that we're going to see today. So we are in latch. In latch, we are active in level. Active level means we are active in this part, not a spark. We are active in this part, level. Active. Level of what? Level of enable. This is still one from last class. I just wanted to repeat those things to come back to explain what we're going to do today. Today we're going to talk about D-latch and D-flip-flop. We have, okay, so let's see what are those things. Okay, good. So we had this latch RS. And we put a control here. We said, okay, so let's put another control here to have enable. But one of the things that was in this diagram or in this circuit is that R and S not supposed to be equal. However, if they both be 1, it acts as a memory, but they're not supposed to be 0. But right now we have enable, and enable is 1, it already made this to 1. So we have the memory already. So we don't need to have 1 anymore. So we can make R and S negate of each other to not let them to become equal or 0 anymore. So this means we put a NOT gate here and just have 1 input. Why we need 2 inputs, R and S? We just need to have 1. This makes a new latch called the D-latch. It's called D-latch. So D-latch is actually has 1 D for data and Q bar and enable. That's it. When enable is 1, whatever is D is going to go pass. And when enable is 0, latch act as a memory. So the linear version of D. So if I want to draw the table, okay, anyway, so we have D as the input, we have enable as the input, so, and output is Q and Q bar. If enable is 1, whatever is in data is gonna pass. So this is gonna be 0, and then negate of that is gonna be 1. And if data is 1, because his enable is 1, pass it out, so this is gonna be 1, and negate of that gonna be 0. And if enable is 0, we don't care about data. Whatever is there is gonna stay, like Q0 gonna stay, and Q bar 0 gonna stay. It means memory. So that's the state diagram for the latch. A state diagram because showing a state. So we have 3 states in this case. States are the state. You tell me the states. What is the states? The first one, should maybe we just have 2 states. And still we can say this is act as a reset, and this is act as a set, and this is act as a memory. Same. So still we have 3 states: set, reset, and memory. But this is just for one latch. You have a system of multiple latch. In that case, that state is going to be more than 3. Yes?
I just have a question about like the diagram that you drew.
Yes.
The one that you drew there is all pancakes.
Yes, yes.
But the one that is on like the slide is not.
Oh, yes, that's a good question. Who can answer that? What is this?
No, but like why are they different?
Yes, anybody can say why?
That's an NAND gate equivalent.
They are equal. They are equal. This is exactly same as that. I don't know why this book that I took this thing, I mentioned that last class too. This is De Morgan law. They are equal. That's why I just go with an NAND all the time to be, consistent. But they are equal. This is exactly equivalent to having not and then or. Because A, B bar is equal to A bar plus B bar. That's a De Morgan law. So that's a good question. Actually, I wanted to mention that in the last question. Thank you. Okay, that's great. So this brings up the idea of having D-latch. And D-latch is actually very good bit of memory, 1 bit of memory, but it still has problem of level active. This level active still exists. Level of what? Level of enable. Because when level active happened, in that level, so many things, the system is not 100% stable in that level. We want to make this level shorter and shorter. Okay, let's see what else I want to fill in with now. Any questions about this? More questions? No, let's clean this up. Let's see what, oh, that's a diagram. Okay, later on, they said, what about instead of having enable signal as an input, we put clock. Clock is kind of input that is actually universal for the system. Maybe you have more than one D latch. For example, you have 1 D latch here, 1 D latch here, and if they have enable and have D, so D1, enable 1, enable 2, and D2. This is D latch and Q and Q bar, Q and Q bar. If we want system be synchronized and act nicely and under control, you need to connect these enables to one input that can be clock. the clock is like synchronization, acting synchronized. This kind of delatch called clock delatch or gated delatch. Not the same, it's not that difference, but it makes it more broad that you can use it for when you are doing cascading, you can use that. So instead of having enable, we just connect clock to enable. That's it, nothing else. This kind of latch called gated latch or clocked delatch. Okay, but that is still level sensitive. That's important part. Being level sensitive still is problem. Let's make it up. And this can store data only when the clock is active. So, but level of clock is active, like this. This is not age of the clock, just the level of the clock. Because still the system is level sensitive. So, operation principle, when clock is 1, the latch is transparent. Whatever coming in, going out. And when clock is 0, latch acts as a memory. Whatever is inside, stay inside. So this is how it works. But the problem coming from this part, latch become transparent. When the latch become transparent and everything coming, everything going, when the clock is 1, if this time of 1 is big, imagine clock is so big, this time is the time that the latch is not very stable because everything out is gonna come in if there is a feedback. And that's gonna make race problems later. So that's gonna make a system unstable. So this is something that I'm gonna talk in here. That's called latch timing problem or delatch timing problem. So, or any latch, because latch is the type of memory that is active with level. When we have level activation for a device, we're going to have this problem. Because the level is big enough, and if there is somewhere in the system loop, like that loop, feedback loop, this, in this case, is going to make fluctuation. In the time that the system is active, in this time that is active, that's going to fluctuate. And this oscillation is the result of, race condition or kind of race condition. Okay, so that's problem. Any idea how we can solve this problem? Anything coming to your mind? How we can make that big clock kind of shorter to solve this problem, because this problem coming from the level of clock. If level of clock becomes smaller, it's gonna get solved, no? How we can, from this, we make it this. This is coming with flip-flop. So first we need to design a circuit to make that. So imagine we have a circuit to so imagine we have a circuit that have a NOT or inverter and give the pulse to that. So this is going to invert the pulse. And one time without NAND. Without NAND is going to be faster because of the NAND propagation time. Okay. So you got the idea now. You just need to compare these two. Okay, what happened? We have a delay here. And this delay coming from propagation time of NOT gate or inverter. And that propagation time, we just need to find it. How we can compare these two? Easily, we can use NAND gate. Always for comparing, we use NAND gate, remember? And this is gonna make something like that. So if we pass it to another NOT, it's gonna be like this. Whatever we wanted. It's gonna create those pulses. That's it. That's pulse maker. You made it. Instead of using big levels of pulses, you just can make them shorter. Like using the same problem that you were always worried about, this propagation time, you just used it to make pulses. So this make latch to flip-flop. What make latch to flip-flop? Using these pulses instead of, and this is like edges. It's like saying you have this clock, and instead of using a level of edge clock, you use edge of clock. This is rising edge, for example. Okay, so this is flip-flop. So to make flip-flop, we just need to change that one in the flip-flop. Let me clean this up. You have better picture of that here. So that was the previous D flip-flop. And instead of having direct clock, we use a pulse, a transition detector. Pulse detector is what I explained exactly, similar to that. And compare these two pulses to find this raising edge. And that's gonna make actually flip-flop, de-latch to flip-flop. So difference between flip-flop and latch is triggered by edge, being triggered by edge, being active by edge. That's it. I'm gonna solve most of the problems, like maybe all of the problems, not all of them. Always there is some problems that's not solved. So but that's flip-flop. And flip-flop is the basic of, the flip-flop is basic of so many circuits and memories. Okay, so the table is same as before, the truth table, but for clock, we just consider that is rising edge. Consider to the rising edge. Let's do example. Okay, so imagine the Q was 0 before. Okay, so the decision time is exactly the time that the edge coming. So decision time is here, 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 and here. Between these times, we not change anything. Whatever was before is gonna stay. But that's the main point of de-latch. So simple and very, lots of applications. So the Q was 0, but here, edge coming. Why edge? Because this is edge. This is the decision-making time. So we want to make decision. Q was 0. Here, D is 1. So D and Q are equal. Yet equal. Here, D becomes 0. Do we need to change it to 0? No, because it's not time for making decision. The time for decision is coming here. So here we make decision. What decision? D is 0, so we make it 0. Again, we stay 0. Even though the D become 1, we're not gonna get 1. When I'm talking we, means the register. It means the memory, the Q. Q stay here, even though this is 1, but the clock is not there to make decision. So the clock is making active. So we make decision in this time when the clock coming, and right now check it out. Is Q, if D 1, yes. So we change it to 1. Again, keep going. Even though D becomes 0, we not change. Go. When the time coming, when the edge coming, we check it out. D is 0, so we make it 0. That's it. This is the output of this flip-flop. If the input is like that. You need to know these things. You're going to have questions for your Friday quiz. At least one of these going to come. I'm going to ask you the output. Okay? Any question? This is very easy to understand. Why is easy? Because you just need to see when you make decision. The time that the raising edge raising comes, that make decision. How we make decision? D, whatever is inside D is gonna pass to Q. But D act like very simple memory. And easily you can do that. Okay, so that's enough for this class. Next class, we're gonna talk about JK flip-flop, and then we gotta go for cascading flip-flop to make bigger sequential.